Hello, I'm Sebastian. Welcome to 9 Trees podcast. Today, I will summarize and review the book. Why Machines Learn by Anil Ananthaswamy is a guided tour of the mathematical ideas that make contemporary artificial intelligence work. Rather than treating machine learning as magic or as a collection of code recipes, the book focuses on the core concepts that explain why learning from data is possible and when it can fail. Ananthaswamy, known for clear science writing, connects modern practice to foundational theory, helping readers see how linear algebra, calculus, probability, and optimization come together inside widely used models. The emphasis is not on turning the reader into an implementer overnight, but on building durable intuition about training, generalization, and the trade-offs behind model design. Along the way, it clarifies common buzzwords and reveals the elegant structure behind techniques that power vision systems, language models, and recommendation engines. I will give you key takeaways from this book. Firstly, learning as a mathematical problem, not a mystery. A central theme is that machine learning can be framed as a well-defined mathematical task. Choose a model family, define what good performance means, and then adjust model parameters to minimize error on data. The book highlights the shift from rule-based programming to statistical learning, where the system infers patterns rather than being explicitly instructed. This perspective naturally introduces the difference between training performance and real-world performance, and why the latter depends on assumptions about how data is generated. It also helps explain why simple models sometimes win, why complex models can overfit, and why more data can be as important as a better algorithm. By grounding the discussion in the language of functions and approximation, readers gain intuition for what it means to learn a mapping from inputs to outputs and how constraints, data quality, and objectives shape what the model ultimately captures. This framing demystifies core ideas such as features, labels, loss functions, and evaluation, showing that many modern methods are variations on the same foundational setup. Secondly, optimization and the engine of training. The book emphasizes that much of modern AI progress is driven by optimization, the practical ability to find parameters that make a model fit data. It explores how gradient-based methods underpin training, especially for neural networks, and why computing derivatives efficiently is transformative for scaling up. Readers are guided through the intuition of gradient descent, learning rates, curvature, and the landscape of a loss function, including why training can be unstable and how techniques like regularization and careful initialization help. This topic also covers the idea that optimization is not just math elegance, but an engineering reality, shaped by compute limits and noisy data batches. The reader comes away understanding why training deep models often involves compromises and heuristics, and why convergence to a perfect minimum is not always necessary for strong performance. By focusing on the mechanics of learning, the book clarifies how errors are propagated backward, how parameters are updated, and why small design choices can significantly change results. Optimization becomes the bridge between theory and the behavior practitioners observe when models learn. Thirdly, generalization, overfitting, and the role of complexity. A major question in machine learning is why a model that fits past data can perform well on new data. The book discusses generalization as the core challenge, examining how model complexity, data size, and noise interact. It explains overfitting as learning accidental quirks rather than stable signals, and shows why avoiding it is not just about choosing a smaller model, but about balancing flexibility with constraints. Concepts such as bias and variance, regularization, and validation practices are used to build an intuition for trade-offs. This topic also addresses why modern large models can generalize despite having enormous numbers of parameters, an apparent paradox that has motivated much recent research. The book conveys that generalization is shaped by both explicit constraints, like penalties and early stopping, and implicit ones, like the optimization process itself. Readers learn to think in terms of capacity, inductive bias, and uncertainty, gaining a clearer sense of when to trust a model and how to interpret performance metrics. The result is a more realistic mental model of what learning systems can promise and what risks they carry. Fourthly, probability, uncertainty, and learning from data. Probability provides the language for reasoning under uncertainty, and the book highlights how it permeates machine learning, from noisy labels to stochastic training. This topic explains why data is never a perfect reflection of reality and why models must operate with incomplete information. By connecting learning objectives to probabilistic ideas, readers see how likelihood, distributions, and assumptions about randomness shape model behavior. The discussion illuminates how uncertainty enters at multiple levels: measurement noise, sampling variation, and the inherent unpredictability of some phenomena. It also clarifies why probabilistic thinking matters for calibration, decision-making, and risk management, especially in high-stakes settings. The book shows how many algorithms can be understood as methods for estimating unknown quantities from observed samples, and why the quality and representativeness of samples matters as much as model architecture. This probabilistic lens helps readers interpret confidence, error bars, and the limits of prediction, and it provides context for why some models appear decisive even when they should be uncertain. Understanding uncertainty becomes a key to using AI responsibly and effectively. Lastly, neural networks and the modern deep learning synthesis. The book ties foundational math to the deep learning systems that dominate modern AI, explaining neural networks as layered function approximators trained by gradient-based optimization. It presents how composition of simple transformations can represent highly complex mappings, and why scale, data, and compute have made these models practical and powerful. Readers gain intuition for architectures and ideas that recur across applications, such as representations, embeddings, and the importance of learned internal features. The book also situates deep learning within the larger ecosystem of machine learning, showing what it borrows from older statistical methods and what is distinctive about its flexibility. Importantly, it addresses limitations and open questions: interpretability, robustness, distribution shift, and the gap between benchmark success and real-world reliability. Rather than portraying deep learning as the final answer, the book frames it as a compelling synthesis of math and engineering that still depends on careful problem formulation and evaluation. This topic helps readers connect the abstract concepts of loss, gradients, and generalization to the concrete models that drive language, vision, and recommendation technologies today. In conclusion, this book suits curious readers who want to understand AI beyond headlines, including students, product leaders, engineers from adjacent fields, and anyone encountering machine learning in their work. It benefits the reader by building lasting intuition for how models learn, why training works, and where failure modes come from, making it easier to evaluate claims, ask better questions, and collaborate with technical teams. Compared with many popular AI books that stay at the level of anecdotes or high-level metaphors, Why Machines Learn emphasizes the underlying mathematical structure without turning into a dry textbook. That balance can save readers time by giving them a coherent mental model that applies across algorithms and trends. It is also worth buying because it focuses on concepts that remain stable even as tools change, helping readers navigate new model types with confidence. If you want clarity about optimization, generalization, and uncertainty, this is a practical and intellectually satisfying investment. If you would like to support Anil Ananthaswamy, you can buy the book through the Amazon link I've provided in the podcast description. After reading the book, please let me know what you think and share your thoughts. See you around.